Welcome to this module of Professor Messer's free CompTIA A+ certification training course on bus architectures and expansion slots. I'm James Messer, and in this module we're going to look at the requirements from our CompTIA A+ 220-701. That's our Essentials exam, section 1.2. We're learning all about the motherboard components, and we're going to look at our bus architectures, and we're going to learn about PCI slots, AGP, PCIe, AMR, CNR, PCMCIA. We need more acronyms in our industry, and I'm bringing them to you. We'll also look at riser cards and daughter boards and what those mean too. There are a lot of different bus slots, and these have really evolved through the years, all kinds of different acronyms that you're going to find there. You almost get lost in what all of these mean. But after you go through this module, you'll see there's some very obvious standards, and the names of these standards are pretty straightforward. So as we step through, hopefully you'll understand more about those capabilities. Before we get into the specifics of what all those different bus architecture types are, let's take a step back and talk about why we even need a bus architecture in our computer to begin with. Well, you've got this really city of technology here. If you look top down at a motherboard, it's almost like we're flying over in a plane. There's all kinds of different paths that take place and different connections between these. And you can see places for CPUs. You can see the bus expansion bus itself where you plug in the adapter cards. And if you look very closely at the motherboard, you'll see these little paths between all of these. And that's your bus. That's the way that these different devices communicate to each other. It's a way that you've got paths between these components. You've also got a way to grow your computer this way because you can plug in different components, and now they automatically connect into that bus and can now connect and talk to memory and talk to CPU and communicate throughout all of your system. And this really gives you a way to really expand your computer. This was the whole idea behind creating standardized buses in this computer, is that people could create standardized expansion parts, and you can plug in and know that what you're plugging in is going to work with the bus that's inside of your computer. If we didn't have standardization, there'd be no way that we could create these extra components and the expandability that we have today with these computers. When we start talking about a bus architecture, we also refer to the size of the bus. It's a 32-bit bus. It's a 64-bit bus. And we're referring to it in those number of bits. That means how much we're able to send down all at one time through this bus architecture. The wider the bus, the more we can send through, and obviously the more bandwidth we're going to get if our bus is bigger. We also talk about the bus as the speed that it uses, the clock speed of the bus. The expansion bus has its own clock, so everything going over that bus all runs at the same speed. We refer to these speeds as things called cycles per second, or hertz, which means if we have 1 million cycles per second, that's 1 megahertz. If we have 1,000 megahertz, that's 1 gigahertz. So whenever we're talking about the hertz, the higher number of hertz, the higher number of cycles per second, the more information we can push down that bus. So if we look at the width of the bus and how fast it's going, we're going to come up with a theoretical throughput of just how much traffic we're able to get through that system every second, or every clock cycle as we go through here, every cycle per second. And if we get a lot of throughput, the bigger throughput, the faster your system's going to be. And that's why whenever we look at things like our front side bus in our computer, we want a really fast front side bus because it's going to be able to transfer data between the memory and the CPU as fast as possible. If we really dive in the architecture of our computer, we can see a lot of different buses. The buses are the black lines that I'm using to designate the communications between these different devices. There may be a separate PCI bus, there's an internal bus, there's a front side bus, we were just talking about that one, a bus for the memory. And each one of these may be different sizes, they may be different speeds. You may not need it to be very fast. For instance, something going from your serial port or your parallel port or your keyboard or your mouse doesn't need a very big bus to talk to the South Bridge. It needs just a very small bus. And so you may find that if it's an 8-bit ISA bus, you've got 8 lanes of traffic you can set up here. And lanes is a pretty good name for this, although not specifically for this type of bus, but you'll understand why in a moment. But you got these 8 different 8 bits, these 8 different pieces of traffic can go between these devices all at the same time. If we wanted to double the speed, we found we were using a 16-bit expansion slot. You'll find you can move more traffic between what's on these expansion slots and this controller hub on the other side. So you've got better throughput, you've got faster throughput usually. There's a lot more you can send across that, twice as much than if you were using an 8-bit device. And that's why whenever we're finding what we can fit into an expansion slot, you want to be able to use the biggest expansion slot you can for the type of device device you're plugging into your system, just so you get the most amount of throughput you can possibly get. We first started using these expansion buses in the IBM PCXT, the original PC. It was an ISA bus, an industry standard architecture bus that was 8 bits wide. And the idea is that the manufacturer could make the computer, but third parties could make expansion cards that would fit into this bus and use this industry standard architecture. We could fit and run devices on this bus to transfer traffic at 7 million cycles per second, or 7 megahertz. So if we looked at the amount of this that we could get across, we were using an 8-bit bus at 7 million cycles per second. That meant that we could send 7 megabytes per second through this system. Not a lot of great throughput there, but that's what we had on the original IBM PC. The next computer that came out was the IBM PC-AT. The bus was twice as big. It was 16 bits wide. It still ran at 7 megahertz, which means we were able to essentially double the amount of theoretical throughput. So now you're starting to see how the width of the bus and the speed of the bus really have an impact on just how much traffic we're able to transfer at any particular time. Here's an example of that 16-bit ISA bus that we have here. If the 8-bit buses were a little bit smaller, we added on this extra piece on the end for the 16-bit bus. Right next to it are some PCI slots. They were a different kind of bus, and occasionally you'll see some legacy computers that can support one or the other or both at the same time. You really don't see that much anymore, but if you're opening up a smaller, an older computer that is a legacy system, you'll see these smaller ports and these larger interfaces inside of it. And in some cases, you can use all of them. You can use only one type at a time. It depends on the motherboard manufacturer. To use the bus, you had a 16-bit device. This is a 16-bit interface card that was an Ethernet card. You would simply slide the interface in there. Notice there's a notch there, so you can't put it in the wrong way. That notch designates and tells you exactly the way this particular card would fit in there. You simply position it correctly in the slot and you push down, and now your network interface card is installed. So even if your computer didn't come with a NIC card on the motherboard, it was very easy to use this standardized bus architecture to plug in a third-party interface card, and now we're on our network.